In this video, we're going to take a look at division again. And we're going to focus in on one-digit divisors. And remember, we're talking about a CRA sequence of instruction. So we're going to start with the representation, and really this video is going to focus on that transition to the abstract way of thinking. So we're going to take a look at the problem 742 divided by 3. So remember, in our representation, the first thing we do is we start by modeling our 742. So that's 700s. Four tens and two ones. And then I want to divide that into three equal groups. So I'm going to create some space for my groups, and I'm going to start my division process. And as we work through this, we're also going to work through the algorithm at the same time. So the first thing that we ask ourselves is, well, I've got 7 hundreds, and I want to know how many I can get into each of the three groups. So I can put 2 of those in. And that's going to use up 6 of my hundreds, and I'll have 100 left that I'll have to deal with. What does that look like in our algorithm? Well, what we would be saying is we have 7 hundreds, and we need to divide that across 3 groups. How many can I put with each group? We can put 2 with each group, and we're writing that 2 in the hundreds place, because then 2 times 3 is 6, meaning we use 6 of our hundreds, and we subtract those to find out what was left over. Okay, and that shows we have 1 left over, which is what we had left over here. So you'll recall that I can't divide that 100 evenly across 3 groups as it is, so I'm going to trade that 100 in and give myself 10 more 10s. What does that look like in our algorithm over here? I'm going to cross out that 1, and I had 4 10s, which are now going to become 14 10s. So now I have my 14 10s over here, and I'm trying to get those across 3 groups. So I'm going to put 3 with each group. So that would be these 3, and then 3 here. That would be 1, 2, 3. I'm going to put 3 more in. Oh, I've got a couple extra, don't I? I've got 5 more. So it wasn't 3, was it? I can keep dividing. Let's do a little more division. So why would I do it that way? Because that's the way our kids are going to work through it, right? They're going to think they know how many they need to put in each group, and then they might see that they have some left over. Remember, the key is to continue dividing evenly or placing an additional 1 in each of our groups until we get to a number left over that's smaller than our divisor. So now I'm down to 2. I can't break 2 10s evenly across 3 groups. What's that look like with our algorithm? Well, we can see that we got 4 in each group. So if I have 14 10s and I'm trying to divide those into 3 groups evenly, I can put 4 in each group. 4 times 3 gives me 12, which is what happened over here, because if I put 4 in each of the 3 groups, that uses up a total of 12 of my 10s. That means that I'm going to have 2 10s left over, and that's what we see here. Our 2 10s were left over. Can't divide those, so now I'm going to decompose. That's going to give me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now I've traded those 2 10s in for 21s. What we've done over here is say those 2 10s are going to come over and become 1s, and that's going to give me a total of 22 1s. So now I know, because there's 22, and I'm pretty good with my multiplication facts, I know I can put 7 in each group. That's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7. And that is going to take care of all of my 1s except for one of them. If I put 7 in each group in our algorithm, that means that 7 is going to go in the 1 spot. How many would that use up across 3 groups? 7 times 3 is 21, and that means that I must have 1 1 left over. Can't decompose it, can't share it evenly across 3 groups. So I've got a couple options. One option is to write it as a remainder of 1. Or remember, we discussed in the other video, I could also write it as 247 and 1 that has yet to be divided by 3. So 247 and 1/3. Now this algorithm is referred to by John van der Waal as an explicit trade algorithm. And one of the reasons that I'm using this algorithm is because it matches very, very nicely what's happening with our representation. And it would still match what was happening with our concrete if I was actually doing this with place value blocks and having students physically manipulate them. So I really like this explicit trade algorithm. And it works. It always works. It keeps kids focused on the place value. But it does have a little bit more involved in terms of what's being written over here. And a lot of us are more familiar with bringing down in terms of our long division model, or that traditional method for algorithm. So I want to make that connection yet between the explicit trade and the traditional algorithm so that we can see if we wanted to transition students the rest of the way, how we could do that pretty quickly. So we had 742 and we were dividing that by 3. Remember, we would say how many 7s can I put into 3 groups? I can put 2 in each of the groups. That would use up 6 and give me 1 left over. And then as we would bring down that 4, okay, and that would give us our 14, and now we would start dealing with how many of the 14 tens would go into 3 groups. And really what we're doing here with this 14 is we're keying in here. One of the things you'll notice is that 1 in the hundreds, when it came over, it just gave us 10 more tens. So the 4 became 14. When we're writing that 4 down, or we're bringing that 4 down, now we're saying think about this in the tens column. This is 14 tens. Okay, so you can see that connection pretty quick. Then when we continue on, we would say that 3 goes into 14 4 times, or if I have 14 items split across 3 groups, I can put 4 in each group evenly. That would use up a total of 12 items and leave me with 2 more left over. Remember, we ended up with the same thing here. Then we said that was 2 tens. And so we should take those 10s and trade them in for 1s. 2 10s would give me 22 1s. When the bring down method, or that traditional algorithm, we just bring down that 2. And now since we're in the 1s column, we're thinking about this as 22 1s, which we know 22 1s divided into 3 groups. We can put 7 in each group. That would use up 21 and give us that remainder of 1. Okay. So a lot of times this bring down method, or this traditional algorithm, if we jump there too quick, students don't understand why they're bringing that number down. They have a hard time lining stuff up. The division algorithm is pretty complicated for students as they begin learning that. But one of the things we can do to help deepen their understanding of what's going on is use this explicit trade algorithm to help them focus in on the place value and the actual trading that's going on, so that they can keep the language consistent when they move to this traditional algorithm, if that's what's desired in your curriculum. And this explicit trade algorithm connects perfectly with our CRA approach to instruction, focusing in on that concrete and that representation. The language is very, very consistent to get students to this point, and then we can transition them down to this traditional algorithm if you would like.